Good morning, everybody. Hope you're all healthy and safe at home. So, we are moving on to the final portion of section 9.2. So, section 9.2 was much smaller than section 9.1. It is getting over very fast. So, in the previous section, we discussed about the velocity of a vector function, the acceleration of a vector function, and so on. So in this session, that is the final portion of section 9.2, what we are going to discuss is where are we going to apply all these definitions that we have learned till now. As we have done what is the velocity of a given vector function, we did what is the acceleration, and so on. So in this section, we are going to discuss the application of the vector function. So for that, we are going to study what is meant by curvilinear motion. So let us go to the definition of curvilinear motion in the plane. Curvilinear, the word meaning is motion in form of a curve. So we can see that many projections like the planetary motion, the projectile motion, all these are different types of curvilinear motion, and most of the applications of vector function take place in such type of motion. So in this case, in this portion, we are going to study or analyze the application of the vector function in the projectile motion. So for this, we are given the acceleration due to gravity. We all know that the acceleration due to gravity will be a constant. So we are treating it in the vector form, and it is given by a of t is equal to minus gj. And we have an initial velocity v dot, which is given by v dot cos theta I plus v dot sin theta j, and an initial height s dot is equal to s dot j. That is, the projectile is launched with this initial velocity v dot and from a height, initial height s dot. And we can find, using these two information, we can easily find the parametric equations for the trajectory of this particular projectile. So let us see how we can find the trajectory of the projectile, parametric equations of the trajectory of the projectile. So let us write down what all we have. We are given the acceleration due to gravity by g. We are given the initial velocity v dot was v dot cos theta I plus v dot sin theta j, and we are given the initial height s dot is equal to s dot j. Now using this equation, we will find the velocity vector, because velocity is basically it is r dash of t, and this can be found from integrating r double dash of t dt, or that is by integrating the acceleration vector given to us. So what will be velocity? The v of t will be integral of minus gj with respect to t. What will be the value? It will be, g is a constant, so it will be minus g into t j plus the integrating constant. Now using the initial condition, we are going to find what is the value of c1. We have v of t was found out to be minus gtj plus c1, and we are given v of 0, that is v dot was v dot cos theta I plus v dot sin theta j. So this implies substituting the value of t equal to 0 in this, we get v of 0 is c1. So c1 is v dot cos theta I plus v dot sin theta j, and therefore our velocity function will be v dot, substituting the value of c1 in this equation, v dot cos theta I, combining the terms together, plus v dot sin theta minus gt g. This will be the velocity function. So next we have to find the parametric equation of the trajectory of the projectile. So for that we have to find the vector function or the position function, vector function associated with it. So we have v of t was v dot cos theta I plus v dot sin theta minus GTJ. How can now v of t, we said that it is basically r dash of t. Now what will be r of t? R of t will be integral of v of t with respect to t. That is, we have to integrate the above function, that is v dot cos theta I plus v dot sin theta minus GTJ with respect to dt. Now note that v dot and cos theta are these all terms are constants. So what will be the integration? Integration will be v dot cos theta t I plus v dot sin theta minus sin theta into t. Integral of v dot sin theta will be v dot sin theta into t, since v dot sin theta is a constant, and the integral of gt will be t square by 2, g into t square by 2, so minus g t square by 2 j, and please don't forget our integrating constant. Now we had considered the initial height s dot to be s dot into j. Now s dot is nothing other than r of 0, that is the initial position of that projectile, and this is the position vector. So the initial position was r of 0 is s dot. So substituting the value of t equal to 0, what do we get when t is 0? This term reduces to 0, this term reduces to 0, this term reduces to 0, we are left only with c2. So what do we get? S dot is nothing other than S dot j. We get C2 will be S dot j. So substituting this value of C2 in our vector function, what do we get? We get R of t will be equal to V dot cos theta t I plus V dot sin theta t minus g into t square by 2 plus s dot j. So this will be the vector function, position vector function of the trajectile. So from this, what will be the parametric equation? X will be v dot cos theta into t, and y will be equal to v dot sin theta t minus g t square by 2 plus s dot. So these will be the parametric equations of the trajectory of the projectile that we have discussed. So let us see, and I'll just recall it again. We are given the acceleration due to gravity to be minus gj. We are given an initial velocity v dot and an initial height s dot, and with first we'll find the velocity using this formula. By integrating acceleration we get the velocity, and using the initial velocity we'll find the value of the integrating constant c1, and then we'll integrate the velocity function to get the position vector, and using the initial height we are going to find the second integrating constant c2, and finally we'll obtain that the position vector will be r of t is equal to v dot cos theta I plus minus 1 by 2 gt square plus v dot sin theta t plus s dot j. And from this, the parametric equations will be x of t is equal to v dot cos theta t and y of t is equal to minus 1 by 2 gt square plus v dot sin theta t plus s dot. Now, this is about curvilinear motion in the plane. So as I've mentioned in the beginning of this session, we are going to do the applications of the vector functions. Let us see how we can apply the properties of the vector function. First, what we can do is we can find the height or the maximum height of the projectile. So now we have discussed how to find the parametric equations of the trajectory of the projectile. So with the help of that, we can find the maximum height of the projectile and the range of that particular projectile. So how can we find the maximum height of the projectile? We have to find a t such that y dash of t is equal to 0 and then substitute that particular value of t in the value y of t. That will give us the height of the projectile. And we have to find the range. We have to substitute. We have to find a t such that y of t is equal to 0. In height, we have to find a t such that y dash of t is 0. And to find the range, we have to find a t such that y of t is equal to 0. And then substitute this value in x of t. That will give us the range of that particular projectile. So let's see the example. Example is to find the trajectory of a projectile, and for finding this trajectory of the projectile, what all things we need? First, we need the initial velocity and the initial height. And note that the acceleration due to gravity is 9.8 meters per second, or it can be considered to be 32 feet per second. So in this case, we are using g to be 32. So see that, note that a of t is minus 32j. Then integrating this equation, we get the velocity vector, and the initial speed is given to be v dot is 768 and the elevation theta is equal to 30 degree. So what will be the initial velocity? Initial velocity will be v dot will be 768 cos 30 degree I plus 768 sine 30 degree g. Now cos 30 degree is root 3 by 2 and sine 30 degree is 1 by 2. So cancelling it out, we'll get the initial velocity v dot to be 384 root 3 I plus 384 g. Then using in the example, we are given that the projectile is launched from the ground level. So the initial height will be 0. So s dot is 0. So we have found what is a of t. A of t is minus 32 into j. The initial velocity v dot will be 384 root 3 I plus 384 j, and the initial height is s dot is equal to 0. So using these three equations and by the portion that we discussed just before, we can easily find the parametric equations of the given projectile, trajectory of the projectile. And the next portion, the B part of this example, is to find the maximum altitude attained by this projectile, and let us see how we can do that. Once we know the parametric equations of the trajectory of the projectile, we have x of t is given to be 384 root 3t and y of t is minus 16t square plus 384t. I want you guys to solve this example and verify it. So from this, we need to find the maximum height attained. Now what should we do to find the maximum height attained? Let us recall. To find the maximum height, we have to find a t such that y dash of t must be 0. So we have y of t is given to be minus 16t square plus 384t. Now what will be y dash of t? Y dash of t is derivative of this, that is minus 32t plus 384. So when y dash of t is 0, we have minus 32t plus 384 will be 0. Solving this, we'll get the value of t is 12 seconds. So once we get the value of t, we have to substitute it in y of t to obtain the maximum height. So when t is equal to 12, what will be the value of y of t? Y of 12 will be minus 16 into 12 square plus 384 into 12, that is 2304 feet. And the next portion was to find the range of the projectile. Now let us recall how we can find the range of a particular projectile. To find the range, we have to find a t greater than 0 for which y of t is 0 and substitute it in x of t. So we have y of t is equal to minus 16 t square plus 384 t. So this is equal to 0 implies we have taking t common, we get minus 16t into t minus 24 is 0. So t cannot be 0, so we consider t to be 24. So t is equal to 24 seconds. So the range will be x of 24, that is 384 root 3 into 24. The approximate value is 15,963 feet. So this is how we can find the height and range. And what is the last portion of this example? We are asked to find the impact speed. Now once we know the velocity, we have done in the previous section that the speed would be the magnitude of the velocity. So what will be the value? The value would be v of now we know that v of 24 will be 384 root 3i plus minus 384j, and the magnitude would be square root of 384 root 3 whole square plus minus 384 whole square, and the value is 768 feet per second. So that will be the speed of the projectile, or the impact speed of that particular projectile. So these were the applications of the vector functions, that is to find the maximum height of the projectile and to find the range of the projectile. So that's it for today's session. Thank you. Stay home, stay safe.